Okay, so let's start. Hello to everyone. My name is Shir Abramovich. I'm a master student from Ben-Gurion University. This is the Spectroscopy and Microscopy first session. Shani and Matan, please don't exceed the time of the presentation. It's supposed to be a 15-minute talk and 5 minutes questions. For the audience, if you have any questions, please keep them to the 5 minutes question time. And you can post them in the chat, or you can raise your hand through the raise hand feature in the Zoom. And one last thing, please mute yourself. First, we'll present Shani Alavan from Ben-Gurion University. Shani, good luck. The stage is yours.
Thank you, Shir. Do you hear me right?
Yes, we can hear you.
Okay. So, hi everyone. My name is Shani, and I'm a master's student in Ben-Gurion University. And today I'm going to talk to you about investigating decomposition mechanisms in cold plasma with in situ optical diagnostics. Okay. Wait. Do you see the slides? Okay.
Yeah, we can see the slides.
Yeah. Okay. So, as you know, waste is a global environmental concern growing up each day partially due to the demand of plastic solid waste. Plastic is a robust polymer composed of mostly hydrocarbons, such as high-density polyethylene and polypropylene. It is very important and beneficial, but it does not decay naturally. Therefore, its disposal became a major challenge. So, as you may all know, there are some solutions these days to treat plastics, such as landfilling, incineration and pyrolysis, and recycling. But those solutions are not practical in time. Moreover, plastic consumes a lot of valuable resources and does not achieve any energy recovery. Therefore, there is a need for a new way to treat plastics. So, in recent years, there has been a use in plasma chemistry. Hot plasma, like other thermal technologies, does decompose plastic well, but is wasting a lot of energy to reach such high temperatures instead of directing it to the desired reactions. That's why we're using cold plasma. So in generally, plasma is the four states of matter. It's an ionized gas composed of charged natural atoms, free electrons, radicals, ions, and ground and excited state molecules. The type of plasma determined by the collisions character, where the energy transfers between the free electrons and the heavier particles, which are the ions and the atoms. So one type is called hot plasma or thermal plasma and refers to a thermal equilibrium between the species. So due to high frequency of collisions and high temperatures, the energy can transfer fast between the species, and therefore the decomposition can occur. On the other hand, we have cold plasma, which is far from thermal equilibrium and contains a variety of temperatures, different degrees of freedom, and particles. As you can see here, the electrons are hot, while the heavy particles are cold. And due to low frequency of collisions and electric fields, an electron can accumulate the threshold energy to perform ionization. So together with all of these properties, cold plasma can be a great and promising way to decompose plastic solid waste. Okay, so in terms of the goals and approach, in order to promise the effectiveness of the waste treatment and use the products as energy, we first need to understand the decomposition mechanisms of these hydrocarbons, because in such complex and fast chain reactions, we cannot fully understand the mechanisms unless we will also look for the intermediates and radicals. So that is why we're looking inside the plasma with an in situ tool in order to look for the intermediates and radicals in real time. Here is a nice example that we really like. This is from a paper. You can see here the decomposition of water using nitrogen. So as you can see, there are many products, many byproducts, intermediates, different pathways that we would have known on unless we will look for it. So how do we detect that? We're using optical emission spectroscopy, which is an in situ tool to analyze molecules in a convenient way. When different atoms and molecules relax, light is being emitted in different wavelengths, and this light is being collected and brought into a detector for further analysis, performing an emission spectrum, as you can see here. So when we put different molecules inside the plasma, we get different colors, which is really nice. And we can use that light for different purposes. So each molecule has a unique spectrum, and each spectrum can give us information about the different transitions, different degrees of freedom, and even different temperatures. You can see here two nice spectroscopy examples, one for an atom and one for molecules. So starting from the left, you can see an emission spectrum, of the H atom from the H-Balmer series. For those of you who don't know, the H-Balmer series is when in upper states, electrons drop down into n equals 2 levels and photons are being emitted. So you can see very distinctive peaks, which tells you the species they are, but also by comparing the relative intensities, you can understand something about the population and therefore about their temperature. On the right-hand side, you can see the emission of the OH radical in a specific electronic transitions. You can see different bands of vibrations here and different rotations. And just for overall summary, that slide, those two species are very, very active. And just by looking at the spectra, you can understand a lot about their decomposition by using spectroscopy. Okay, so a little bit about the strategy and system. As you can see, the system is composed of 3 different parts: the experiments, the analysis, and the simulations and modeling, while the idea is working in a loop. The simulations and modeling helps us to ensure the reliability of our system, to improve the efficiency, to design new modifications to our system, but also to limit the margins of work because they are very wide. So here is the plasma reactor. There are several types of low pressure plasmas. Ours is called capacitively coupled plasma. The plasma is being generated between those 2 electrodes by an RF generator, performing an oscillating electric field. So together with the mass flow controllers and the vacuum pump, we can create a bunch of different conditions and control the power, the pressure, and the gas composition. Moving on to the analysis. So in the in situ analysis, we have 2 optical fibers that collects the emission from the plasma reactor, directing it to different detectors and a computer softwares. Why we have 2 detectors? Because the flame mass detector is more like a fuller picture of the spectrum, while the Hori-Bus CCD camera is a very high resolution detector that's composed from 2 gratings. Okay, recently we have added a new tool to our system, an ex situ tool called the residual gas analyzer, which is a little mass spec for the outcome products. So the RGA is helping us in cases in which some molecules don't emit light in the UV-Vis area, or some molecules emission is overlapping with others. So basically using all of these instruments simultaneously is helping us to get information, complete information for the system and the experiments. Okay, so starting with the results, let's start from easy carrier gases, nitrogen. Unlike other carrier gases, nitrogen does involve in chemistry. Moreover, nitrogen's emission can be divided into bent systems like other many molecules. So here things started to get more interesting. We can start to ask questions like where the energy is going. Is it going on performing a chemistry such of this NO molecule over here, or is it going on different degrees of freedom, such as this system, the second positive system that you can see over here. So if we zoom in to the higher resolution detector, we can see the second positive system of nitrogen, a specific electronic transitions with different vibration bands. By comparing those vibration bands, we can actually obtain the vibrational temperature, which is very important because we can understand how much energy is being put in different degrees of freedom as the function of the plasma conditions. Okay, moving to more interesting things, the hydrocarbons. We chose alkanes and alcohols to be our source of hydrocarbons because they're accessible, they're volatile, and they're a good representative of simple molecules. They're basically the base of the pyramids towards the relevant complex polymers that we will investigate later. So we conducted two experiments separately, both with argon as a carrier gases. And we noticed that their emission in those areas over here looks pretty much the same. Maybe the intensity looks different, but the band's positions are in the same place. And it took us a long time to understand that those are different bands. In the methanol, we got the CO band, that's called the CO angstrom band. And for the hexane, we got the C2 band called the C2 Swan band. So the high resolution CCD camera is helping us in cases where two molecules emission are falling in the right exactly place, and it's hard to distinguish between them. So it's very helpful. Okay, here's a nice glance for our simulations and modeling that we do. So in order to do a simulation, we first need to calculate the quantum constants for a specific molecule or transition. And then put it in a program called PGOFER, which helps to simulate rotational, vibrational, and electronic transitions.
Shani, you have 5 minutes left.
Okay. So here you can see a nice simulation of the 0-0 band of nitrogen. Up here, you can see an error bar of this individual temperature fitting. So the temperature is low as we want it to be, and so is the standard deviation. So this means that the simulation went successfully. On the right-hand side, you can see a model that another member of our group did in a program called COMSOL, which helps to predict many physical phenomena. On the blue here, you can see one of our peaks of argon, its intensity, that comes in a good correlation with the predicted number of density. To improve our efficiency, but also a validation check to each set of results. Here's a nice figure of how the temperature changes as a function of the plasma power for the 0-0 band that I was just talking about. We do the same thing for different bands, different molecules, and change the different parameters. So this is very helpful. Okay, moving on to a different subjects, I just wanted to tell you a story. So each time we introduce water samples inside our plasma reactor, we get the usual products, which is an H atom and OH radical. But things get a little bit more exciting when we first scanned with the RGA, a mass scan, and we first noticed that we have a huge band of H2 molecule. And that was very weird and bizarre because we have never seen any H2 emission. So we went looking for it. And the reason why we haven't seen it is because first, the H2 emission is very weak. But second, because it's falling at the same wavelengths where we have the first negative system of nitrogen. And since we constantly have an air leak, we keep seeing those bands of nitrogens. So that's why we haven't seen the hydrogen. So we went looking for it very carefully, and we found it, and we were very happy. But next task was to quantify how much H2 we produce from decomposing water. So we have tried many, many methods, but none of them gave us any reasonable results based on what we see in the OES and in the RGA. So we figured out that the best way to quantify how much hydrogen we have will be to actually perform a calibration curve with real amounts of hydrogen, and then put our results in it to see where it falls. So we borrowed this H2 generator from another group, and we made two experiments. The first one was to measure the water evaporation rate, but weighting how much water evaporates in time. We got the moles per minute and converted it to SCCM, which is flow. Then we produced a calibration curve from known amounts of hydrogen with different flows of argon. We put the real signal of water decomposition in it. And finally, we got the production is more so 6.5 SCCM. So from the left here, you can see the H2 yield, which tells you how much water converted into hydrogen. We got almost 30%, which is pretty amazing considering the fact that we didn't even know that we produce hydrogen. On the right-hand side, you can see the energy yield that tells you how efficient your system is. So we got a 0.36 gram per kilowatts hour, which is reasonable energy yield. Not that great, but this is very preliminary results. And we think that we can even produce more hydrogen. But even if we're not, we're totally happy with those numbers because we just made a recovered nice byproducts just together with our actual goal, which is to decompose plastic waste. So we were very pleased with that. And that's it for today. Thank you very much for your attention. If you have any comments or questions, please ask me.
Thank you, Shani. It was very interesting talk. Someone have any questions? No. Okay, so I have one question actually about the graph you showed of power plasma against temperature. So I was wondering why the graph is not linear, why we don't see an increasing in the temperature with the increasing in the power, in the plasma power.
Okay, so this is very interesting. We also thought that if the plasma power will raise, also the temperature will raise, but we got many graphs that looks like that, and we still don't know what the reason of it, but that's what we want to explore because this is not a conventional thinking.
Okay.
Yeah.
Okay. Hopefully you'll find an answer. So next we'll present Matan Menachem from Weizmann Institute. Matan, good luck. You can start.
You're muted.
Matan, you're muted.
Okay. Okay. So hi, my name is Matan Menachem. I'm a PhD student in Omer Yafes group in the Weizmann Institute of Science. And today I wanted to present to you my work on strongly anharmonic octahedral tilting in 2D perovskites. Now, in order to talk about 2D perovskites, we have to start talking about 3D perovskites first, which I'm sure they need no introduction, but they have the unit formula of ABX3. And they reorganize in this crystal structure that you see here of a corner sharing network of octahedra, where the metal B cation sits at the center of the octahedron, formed by the X halide anions, and the A cation sits in the hole in the between the octahedra. Now, when the A cation is too big to fit the structure, it breaks the structure into a two-dimensional one, where we have layers of the corner sharing octahedra separated by a bilayer of the organic amide. Now, specifically, I'm going to focus about the lead iodine perovskites, where the inorganic layer is a octahedra of lead iodine. Now, immediately from these structures, we can see that the structures of 3D and 2D perovskites are extremely related and extremely similar, which is our starting point. Now, why should we care about 2D perovskites? They form a naturally occurring multi-quantum structures, meaning that as a result, they exhibit strong excitonic features even at reasonable temperatures, as you can see here, for example, from the absorption spectrum of a 2D perovskites at different temperatures. And for this reason, they are a great playground to study basic exciton physics, which excitons are the most basic many-body problem that we can study, which we would normally have to go to very, very low temperatures in order to see. Moreover, the two-dimensional perovskites exhibit strong coupling between excitonic and electronic properties and their structural dynamics, mainly their vibrations inside the material, which again, you can see here in the temperature-dependent absorption. So for starters, at the low temperature, we can see what is called the absorption fine structures due to coupling to vibrations. And as we increase temperature, we populate more and more vibrations in the material, and the electronic properties change, exactly due to this coupling. Now, moreover, of course, these materials are candidates for photovoltaic applications such as broadband LEDs. and perovskite-based solar cells. And in these materials, the perovskites operate on a high temperature, close to room temperature, where their performance is determined by their structural dynamics. So I'm going to focus mainly on the 2D perovskites butyl ammonium lead iodine, which you can see here the crystal structure. And our method of choice is Raman scattering. So just to begin, let's talk a little. And we wanted to compare it to the structural dynamics of the 3D perovskites. It's a 3-dimensional counterpart methyl ammonium lead iodine. Now, just to start the discussion, let's talk about Raman scattering. This is the example of a spectrum of Raman scattering, where the x-axis is the frequency of the vibrations and 0 is our laser line. Now, to first order, we assume that each peak here is a vibration, it's a standalone vibration. They don't interact at all. Every peak has a frequency and some full width half max mentioned by this gamma here, which is related to the lifetime of the phonon, of the vibration. Now, as we increase temperature, we would expect to see, so in first order, we would expect to see nothing because there's no temperature dependence. But in real life, we see shift of the frequencies and broadening of peaks, which are related to modes interaction, vibrations interacting with one another, affecting one another. And sometimes we even see dramatic changes in the spectra, which are related to phase transitions. Oh, shit, sorry. Let's start the comparison of the structural dynamics. So as I said, I started by comparing the temperature-dependent Raman scattering of the 2D perovskites butyl ammonium lead iodine and its 3-dimensional counterpart methyl ammonium lead iodine. On the right, you can see the corresponding A cations. The 2D perovskite is the blue curves and the 3D perovskite is the red curves. Now, if we focus specifically on the low temperature range, we see that their structural dynamics is very similar. We see the same number of peaks in relatively the same positions with comparable widths. Of course, there are changes because it's not the same. And we also see that there's that the spectra are well behaved. Every peak is a Lorentz oscillator. It's a Lorentzian shape. They blue shift and sharpen as we go down in temperature, which tells us that their structural dynamics is very, very similar. Again, it makes sense because of their related structures and because they both have the same, they both have orthorhombic symmetry at this temperature range. Now, as we increase temperature to 200 and 300 Kelvin, we of course see redshifting and broadening of peaks as would expected, but we also see dramatic changes in the Raman spectrum, indicating phase transitions. So at 200 Kelvin, methyl ammonium lead iodine has already undergone a phase transition to a tetragonal phase. And we see that the Raman spectrum is very broad and features are undistinguishable. And at 300 Kelvin, butyl ammonium lead iodine also undergone a phase transition with a similar effect on the Raman spectrum, where everything is broadened and features are highly undistinguishable, but its symmetry didn't change. It remained orthorhombic even at the high temperature phase. Now, again, all of this tells us that the structural dynamics of methyl ammonium and butyl ammonium are related, are similar, and that our initial hypothesis that the comparison has merit is valid, and we can go on with the comparison. So we went to a deeper analysis using a method called polarization orientation Raman scattering, where we excite our sample with a linearly polarized light, and then we collect the backscattered light in either light that was scattered either parallel or perpendicular to the incident polarization, and we follow the modulation of the intensity of each peak as we rotate the incident polarization, which is what you see here, the modulation of intensity of each peak of the peak as a function of the polarization angle, which is the x-axis. The red curves are the parallel configuration and the blue curves are the perpendicular configuration. And by fitting it to a model, which is the solid curves here, we can extract the mode symmetry. And you can see here for the 2D perovskites, you have an AG and a B1G mode. And for the methyl ammonium lead iodine, we have a B2G mode and an AG mode, which now allows us to compare not only the frequencies of the modes, say whether they are in close proximity, but also their symmetries. And we found great correlation between the frequencies and the symmetries of the materials. Now we've asked our collaborators to also perform density functional perturbation theory and calculate the atomic displacements of the modes. And when we compared the already compared modes and compared their atomic displacements, we saw a great match between the modes, saying basically, so as you can see here, an example, one mode of butyl ammonium lead iodine and its comparable mode in methyl ammonium lead iodine exhibiting a very similar atomic displacement. And here in figure C, you can see the large contribution of the butyl ammonium to that motion, which tells us that not only the frequencies, but the symmetries and the atomic displacements in both materials is very similar. So up until now, we talked about the low temperature phase. What about the high temperature phase? What happens when we undergo a phase transition? So going back to the Raman scattering of butyl ammonium lead iodine, we see that the spectra before the phase transition and above the phase transition are very, very unsimilar. They are very different. But if we look very, very closely at the low frequency range, we see some similarities. Now, this makes sense. If we look at the XRD below and above the phase transition, we see that the structures are similar. This phase transition was already reported as an order disorder phase transition, where the organic cations align in parallel above the phase transition. But as you can see, the symmetry, the space group of the structure remained orthorhombic before and after the phase transition, which probably leads to the similarities. So what I did, I followed the peaks along the entire temperature range in the low frequency, in the low temperature phase and above the phase transition. And I followed their symmetries as well. And I found a great correlation between the modes in the high temperature phase and the low temperature phase, suggesting that this phase transition is indeed mainly dynamics. Now, moreover, when I looked at the mode assignments done by DFPT, we saw that most of the modes persisting in the spectrum of the high temperature phase, most of them consist of an octahedral tilting motion around the crystallographic B axis. Now, if we go back to the XRD, we see that in the lead iodine layer, the most abrupt change, the most obvious change in the XRD is the octahedral rotation around the B axis.
Matan, you have 5 minutes left.
So we see that the modes and the symmetries did not change much during the phase transition. The phase transition is related to octahedral tilting, and the phase transition is mainly dynamics. So we want to understand the phase transition of 2D perovskites in the context of 3D perovskites, what we know already on methyl ammonium lead iodine. So let's talk a moment very briefly on the phase transition of methyl ammonium lead iodine. Currently, how we understand it is that the atoms in methyl ammonium lead iodine fill a double well potential, as you see here in the bottom, where the x-axis is an amplitude of an octahedral rotation, and the y-axis is energy. Now, at low temperatures, the atoms are confined to the bottom of the wells, meaning that they rotate in small amplitudes around a finite octahedral rotation. And the structure that we have is some low symmetry structure, in this case, a tetragonal structure. As we increase temperature, we populate more and more vibrations, the amplitudes of the motions increase, and the atoms start sampling more and more of this double well potential, until at some point, there's a possibility to cross the barrier of the double well potential. The atoms sample all of the double well potential. Now, in this case, the dynamics is still governed by the bottoms of the well, as you see by these probability curves here. But the structure, the one that we measure in XRD, which is the average structure of all of the configurations of all these octahedral rotations, is the untilted one, the one at 0 octahedral tilt, giving us a higher symmetry, in this case, cubic phase. But how is it related to butyl ammonium lead iodine? The symmetry of butyl ammonium lead iodine doesn't change during the phase transition. So going back to the XRD of the high temperature phase, we see that the octahedra have a small finite tilt of the octahedra around the crystallographic B axis of about 6 degrees. This tilt is what breaks the symmetry and keeps it at the lower symmetry, orthorhombic symmetry, after the phase transition. If we still adopt the double well potential model, this tells us that one of the wells are not equivalent. And the way we understand it now is that the atoms still feel a double well potential related to some octahedral tilting motion, but one of the wells is more stable than the other one. Now at the high temperature phase, when we average all of these configurations, the average structure is not the untilted one, but a slightly tilted one, giving us back the same symmetry we had at the bottom of the well. Now, what would stabilize one of the wells compared to the other? This would be the strong hydrogen bonds between the amine group in the butyl ammonium and the halide anions, the iodines. If this octahedral rotation doesn't involve a large motion of the organic cation, it would stabilize one configuration much more compared to the other one, giving us the tilted high temperature phase. So for conclusion, generalizing this concept to 2D perovskites and the three-dimensional counterparts, we saw that structural dynamics of 2D halide perovskites and their three-dimensional counterparts are strongly related, meaning that studying the structural dynamics of 3D perovskites would greatly help understanding the 2D ones. And the order-disorder phase transition in 2D perovskites involve activation of strong octahedral tilting motions. With this, I would like to thank my group members, my collaborators in UPenn and in the Weizmann Institute of Science. I would like to thank the IVS committee for allowing me to speak today, and thank you all for listening. Questions?
Thank you, Matan. Any questions? Okay. So I have one question. I wanted to ask you if you can generalize your claim to other two-dimensional perovskites. Did you measure other two-dimensional perovskites?
Yes. So in general, you can see my slide right there. So we have measured another perovskite, which I left out of the presentation. It's phenethyl ammonium lead iodine, where the organic cation has a conjugated molecule, and the interactions between organic molecules is much stronger. What we have seen in the Raman is that it exhibits no phase transition, and its symmetry is much, much lower, telling us that basically the strong interactions, or as the interaction increase in between the organic molecules, it reduces the symmetry or dictates more the symmetry of the crystal and denies phase transitions, for example. Now, in this case, we couldn't do the FPT calculations or any of this polarization orientation Raman because of the very low symmetry. What I can generalize is the fact that people have measured, I also measured other alkyl ammonium perovskites, the pentyl ammonium and hexyl ammonium, very preliminary results, but showing very similar trends. And other people have measured and did molecular dynamics calculations on other alkyl ammonium chains, and they all exhibit the same concept of phase transition. Most papers focused on the organic molecule, but again, our gives this approach that the same phase transition, the same order-disorder concept happens in the inorganic layer and is related to octahedral tilting.
Okay, thank you. Other questions? Okay, so if there are no more questions, we'll finish the session. Thank you for listening. Bye-bye.
Bye.